Okay, so we will continue with the Enol and Enolates chapter. And now we're going to talk about the enolization and the enol content. As you know, we have when we have an enol, it will tautomerize into the ketone. And we're going to talk today about some compounds where the enol form is more stable than the ketone. What we covered in a previous course, when you have an enol, the tautomerism will happen automatically to the ketone because the ketone is more stable. So tautomerism is the interconversion between two structures that simply differ by the placement of an atom or group. And this is what we have when we go from the enol to the ketone or from the ketone to the enol. This process is slow in neutral solutions. However, in the presence of acid or base, the process will be much faster. So basically what you are having to go from the ketone to the enol, you are abstracting an alpha hydrogen, you're forming a C double bond C, and the oxygen is picking a proton. Now this process can be done under acidic conditions or under basic conditions. Under acidic conditions, the oxygen of the carbonyl will pick up a proton, and that will get you the protonated form. There is a plus charge here. And then the water will pick up an alpha hydrogen. You will form a C double bond C, and the double bond will move to neutralize the plus charge, and that's how you will get the enol. While under basic conditions, what you are having is that the hydroxide ion will pick up the alpha hydrogen, and you will form the enolate. Now, this enolate is in resonance with this enolate. So you have the O minus. O minus will pick up a proton from water. So under acidic conditions or under basic conditions, you can form an enol. Now, we need to know about the enol content. If we are looking at an equilibrium constant here between the keto and the enol is very small in terms, or the amount of enol is very small at equilibrium. And that has to do with the fact that the keto is more stable. Usually it is in the order of 45 to 60 kilojoule per mole more stable. However, if you look at different examples, you are going to see that the enol is more stable than the keto. Before we go that, if you look at acetaldehyde, to the equilibrium or the tautomerism between the acetaldehyde and its enol form, the K is 3 times 10 minus 7. Between acetone and its enol, the K is 6 times 10 minus 9. This means that you are having the direction of equilibrium to be towards the keto rather than the enol form in both the acetaldehyde as well as the acetone. However, if you look at 2,4-cyclohexadienol and you are looking at the equilibrium constant between the keto and the enol form, you will see that the keto is less stable than the enol. And why is that? Because you are having an aromatic ring here. The enol form, now you are having an aromatic ring. So that is going to make the enol to be more stable than the ketone. And that is why the direction of equilibrium is towards the right. Now, if you look at beta diketone, so if we are looking at 2,4-pentadienol, and we are looking at this equilibrium constant, depending on the solvent, we can see that we can favor the enol. For instance, if you put it in carbon tetrachloride, the equilibrium constant is 29, which means you are having the enol to be more dominant than the ketone at the equilibrium. I'll get back to this K in a second, but why do we have the enol to be more dominant than the ketone? Because when you are having this enol, you can have a hydrogen bonding between the oxygen of the carbonyl and the proton, and you are having the 6-member ring. Now this happens in carbon tetrachloride, and you are having the K to be more than 1, which means that you are having more enol than the ketone. However, if you are looking at this equilibrium in water, you will see that K is less than 1. Can anybody provide an explanation for this? That's correct. Because in water, what you are going to have, hydrogen bonding between the water and the two carbonyls. In carbon tetrachloride, you do not have such hydrogen bonding. So the hydrogen bonding in the beta diketone in carbon tetrachloride will favor the enol rather than the ketone. When you add water, now there will be hydrogen bonding between the solvent and the ketone, or the keto groups, and you will not get the enol form. Rather, you will have the ketone. We'll carry on. Alpha halogenation of aldehydes and ketones. Well, this is a very interesting reaction. If you are having an aldehyde or a ketone, and you add X2 in the presence of traces of acid, you can achieve the alpha halogenation. So you are putting a halogen at the alpha carbon. This reaction works well if X2 is Cl2 or Br2 or I2. This substitution is specific for the replacement of an alpha hydrogen. It is catalyzed by acids. One of the products, in fact, is an acid, so it is autocatalytic. As long as you have traces of acid, since the side product is an acid, the reaction can keep going. The reaction is not a free radical mechanism. You do not have any radical. In fact, the reaction involves the enol of your ketone or aldehyde. Let me go over examples, and then we'll go over the mechanism of the reaction. When you have cyclohexanone and you are adding you're adding Cl2 in water, you can achieve the alpha halogenation. So you are getting the Cl at the alpha carbon. Another example, when you are having the cyclohexyl carbaldehyde and you are adding Br2 in chloroform, you are achieving the alpha halogenation. You do not replace this hydrogen. You do not replace this hydrogen. You do not replace the hydrogens here. You're only replacing the alpha hydrogen. And you're getting it in a very good yield. In 80% yield, you are getting the alpha bromination. Facts about this reaction. So some experimental facts. This reaction is specific for the replacement of an alpha hydrogen, only the alpha hydrogen. Second, equal rates for chlorination, bromination, and iodination. Third, it's first order in ketone, zero order in halogen. So what do we conclude? The rate determining step does not involve the halogen. Correct? In fact, this is proven with these two facts, because you have equal rates for chlorination, bromination, and iodination, and also it is first order in ketone, zero order in halogen. So interpretation, there is no involvement of the halogen until after the rate determining step. Fine. Two stages. The first stage is the formation of the enol, and then the enol will displace the halogen. So if you are having a ketone, it is a slow process to go to the enol, and then this is fast. The enol will attack X2 in a fast process, and you achieve the alpha halogenation. So how do you do that? Well, you have your enol, and then this will come back. The double bond will attack the bromine, and Br minus is going to leave. So you are having the conjugate acid of the alpha halogenated product, and then Br minus will simply abstract this hydrogen. And remember that this structure has a resonance structure, which is this one. Of course, this is a more stable resonance structure. So in the last step, Br minus just picks up the proton, and you will achieve the alpha halogenation. So when you are having this enol, or when you are having the aldehyde or ketone in the presence of traces of acid, you can get the enol, and then the enol can attack the halogen, and you will achieve the alpha halogenation. However, the reaction will be much more interesting if you perform this reaction under basic conditions. And then the name of the reaction will be called the haloform reaction. In fact, the haloform reaction is a very useful reaction when you are having a methyl ketone and you are trying to identify that methyl ketone in the lab. So you are having an unknown, and your unknown is a methyl ketone. You can do what's called the iodoform test. Why iodoform? Because you will get iodoform as a side product. Bromoform, you will get bromoform as a side product. Well, and that precipitates, and it has a color, and a yellow to orange color. So you can see it very easily. So those who are chemistry majors, you will have in your senior year to identify an unknown. And basically, the first thing you can do is an iodoform test. It takes you, you're knocking your head, you're a chemistry major student. You will do it in like a minute. So you will do the iodoform test. If it is positive, right away you know that your unknown is methyl ketone. So you already identified that it is a ketone and you have a methyl group. So you already identified CH3, C double bond O. You still need to identify the second part. And it takes only just a couple of minutes to get all of this done. Why? Under basic conditions, you have the halogenation of the methyl group. You will do it the first time, then the second time, then the third time, and then you will cleave the CBr3 or the Ci3 or the Cl3. So it's called the haloform reaction because chloroform, bromoform, or iodoform are products in this reaction. So what do we have here? I'm going to give you an example, then we will go over the mechanism. Let's say I have this methyl ketone, and you are adding Br2, sodium hydroxide, and water. But you are going to have, CHBr3 plus the carboxylate. So the product of methyl ketone plus Br2 and sodium hydroxide and water is a carboxylate, not a carboxylic acid. A carboxylate plus bromoform or chloroform or iodoform, depending if you are adding Br2 or Cl2 or I2. Now, if you add H plus to the mixture, you will be protonating your carboxylate into a carboxylic acid, and you will still have the CHBr3, the bromoform. Now, this reaction is useful if you only have one type of alpha hydrogen. If you have two types of alpha hydrogens, you are not going to observe this reaction. Why? Because you could have an alpha halogenation at this carbon or at this carbon. So this reaction works very well when you only have one type of alpha hydrogen. In other words, you have a methyl, C double bond O, and a group right here that does not have an alpha hydrogen. So it works very well if you are having the tertiary butyl methyl ketone, or if you are having an aromatic methyl ketone, but it does not work well when you are having this. So you're not going to get the precipitate, the haloform. So what's going on here? Well, when you are adding X2 and OH minus, if we are doing the first one, well, in the presence of OH minus, you are adding hydroxide ion, you are going to form the enolate. So you're having R, C, O minus double bond CH2, and then you're reacting it with Br2. So you are having 1, 2, 3. So you're getting R, C, double bond O, CH2, Br. Now, you're having these hydrogens that are acidic, and now you are getting these two hydrogens closer to bromine. Would these two hydrogens be more acidic or less acidic? more, because now you are putting an electronegative atom. So this will happen again, and you go to RC double bond O CH Br2, and then a third time. So you are having hydroxide ion, Br2, and water, and then it will happen another time. And you're getting R, C, double bond O, C, Br3. Now what happens is a nucleophilic acyl substitution. The hydroxide ion now will attack the carbon, and you're getting O minus. So you're having R, C, O minus, CBr3, OH, then O minus will kick out the CBr3. So what you are having then is R, C double bond O, OH plus C, Br3 minus. But then you are having an acid-base reaction between the carboxylic acid and the CBr3 minus, and what you will form is the carboxylate plus the bromoform. All of this happens upon adding Br2 and hydroxide ion. So you're having the first alpha halogenation, the second alpha halogenation, the third alpha halogenation, and then you are having a nucleophilic acyl substitution. The hydroxide ion is attacking the carbonyl, and then there is an acid-base reaction. Now, if you drop H+, you will be protonating the carboxylate into a carboxylic acid. So you will get the bromoform plus the RC double bond O, OH. So what you are having here, methyl ketone, X2 and hydroxide ion, the first alpha halogenation, the second alpha halogenation, the third alpha halogenation. Why is this happening? Because these hydrogens are becoming more acidic as you put an electron withdrawing group. In fact, the acidity here, if you look at the pKa value of this hydrogen 19.1, for this hydrogen 14.3, for this hydrogen it is 11.9. So you are having that hydrogen to be more acidic, and you can form the enolate faster. And then you are having the hydroxide ion to attack the carbonyl. You are getting this intermediate. This is slow. Then O minus will kick out the CX3, and you will get the CX3 minus plus the carboxylic acid, and there will be a fast acid-base reaction to form the carboxylate plus the haloform. If you take this mixture and you add an H+, you will be acidifying the O minus. Now what about carboxylic acids? If you are having a carboxylic acid, what we just did was the alpha halogenation of an aldehyde or a ketone. What we want to address now, can we achieve an alpha halogenation in a carboxylic acid? So if you are taking the carboxylic acid plus X2 to get the alpha halogenation, well, we agreed in the previous section that you are having the enol to attack or the enolate to attack, whether you are doing it in acidic condition or basic conditions. If you have a carboxylic acid, so you want to do it under acidic conditions. If you do it under basic condition, there will be an acid base between your carboxylic acid and the base. So the question then comes to the following. Do you have an enough enol content in the carboxylic acid so that the enol will attack the halogen like we did in the previous section? Well, the answer is no. You do not have an enough enol content in a carboxylic acid, and the reaction will not work. If you add just Br2 with the carboxylic acid, the reaction will not work. However, if you add Br2 and phosphorus or phosphorus tribromide, so you are adding Br2 plus P or Br2 and PBr3, the reaction will work well. And you can achieve the alpha halogenation. The combination of these conditions are called the Vollhardt Zielinski reaction. So the Vollhardt-Zielinski reaction is simply the alpha halogenation of a carboxylic acid, and that can be done by adding Br2 and phosphorus. For instance, if you are having the benzyl carboxylic acid and you are adding Br2 in the presence of phosphorus trichloride and benzene is solvent, you can get the alpha bromination. Here is another example. You have butanoic acid and you are adding Br2 and phosphorus, you can achieve the alpha bromination. Now this reaction is very useful. Why? Because you can take this bromo and you can have functional group transformation. For instance, you can have a nucleophilic substitution now by adding potassium carbonate water, and now you will hydrolyze this bromine and you are getting a hydroxyl group at the alpha carbon. Another example, you can take the alpha halogenation product of a carboxylic acid and you add ammonia and water, and now you are getting the amino group at the alpha carbon. In fact, this can be used in the synthesis of amino acids. This approach can be used to synthesize amino acids. Now, why does this work? Well, in the Vollhardt-Zielinski reaction, you are adding PBr3 or you are adding PCl3 to the carboxylic acid. What you are doing, in fact, you're converting the carboxylic acid into an acid halide, an acid bromide or acid chloride if you are adding PBr3 or PCl3. The enol content of an acid halide is higher than that of a carboxylic acid. So when you are adding the PBr3 or the PCl3, you are getting the acid chloride or acid bromide. The enol content is higher than the enol of the acid chloride is attacking. You will get the alpha bromination, and then there will be a hydrolysis of the acid chloride or acid bromide back into the carboxylic acid. Here is another set of conditions for the Vollhardt-Zielinski reaction. You add first thionyl chloride, which means you are making the acid chloride. Then you are having NBS, a source of bromine in low concentration. And then you are adding water, which means you are hydrolyzing the acid chloride. With that, we are going to go into a new section, a very interesting section, which is the chemical and stereochemical consequences of enolization. If you take cyclopentanone and you add D2O, excess of D2O in the presence of KOD, what you are going to observe is the cyclopentanone 2255D4. Every alpha hydrogen is being exchanged for a deuterium. Why? Well, when you are having cyclopentanone and you are adding the O minus, you are going to form the enolate. And then this enolate is going to abstract the deuterium from D2O. And it will go back to the keto form. And now you have substituted the alpha carbon with one deuterium. Then you do it the second time, the third time, and the fourth time. And you will lose all hydrogens, and now you are having them as deuterium. Another very interesting consequence for enolization is the loss of chirality. If you are having a chiral center at the alpha carbon, so that alpha carbon is chiral, and you are adding H2O plus, only H2O plus, or you are adding H2O and OH minus, you started with 100% R, you are going to have racemic mixture, 50% R, 50% S in both cases. Why? When you are adding an H3O plus, you're getting an enol. You recall from chapter 7 of Chemistry 211. If you are having achiral starting material, it's going to lead into a chiral product. You might have chiral center, but you are going to have a racemic mixture. So when you are going from the ketone to the enol, you have destroyed chirality, because now you have C double bond C, you have achiral starting material. But then the enol is going to go back to the ketone because the ketone is more stable, and then you can have the attack to happen in both ways. So you are going to get a mixture. 50% R, 50% S. So when you are having the ketone and you are adding H+, you're having the enol. If you are adding a hydroxide ion, you're forming the enolate. Now this enol, when it goes back to the ketone, it can go 50% to the R, 50% to the S. Do you have any questions? Before we go that, the results of rate studies, they are equal rates for racemization, for hydrogen deuterium exchange, for bromination, for iodination. So the enol is intermediate, and its formation is the rate determining step. So when you are having such a chiral center and you are adding hydroxide ion or an acid, you're going to get a racemic mixture. If you are adding deuterated hydroxide ion or deuterated water, you are going to have hydrogen deuterium exchange. How can you get hydrogen deuterium exchange? You must have an enol. The same, if you are having bromination or iodination, you are having equal rates, which means that the reaction must happen, or the iodination or bromination must happen after the rate determining step. So all of these facts, they are supporting the existence of an enol under acidic conditions or enolate under basic conditions. Okay, the interesting part right now, if you have an alpha beta unsaturated aldehyde or ketone, so you have C double bond O, R1, CH, double bond CH2. This is called an alpha beta unsaturated aldehyde if R1 is hydrogen, or ketone if R1 is an alkyl group. Now, if you have a nucleophile, this nucleophile can attack either the carbonyl, and you are having O minus. So that means you are forming CH2 double bond CHCO minus, which will be protonated. So you are having OH R1. And here is your nucleophile. Or you can have the CH2 double bond CH C double bond O R1, and you have your nucleophile. Then this nucleophile can attack the beta carbon, and you will move the electrons over here, and you will get the O minus over here. So you are getting eventually, well, before we go into the final product, you are getting the CH2 nucleophile CH double bond C O minus R1. Then this R1, this O minus is going to be protonated, so you're having OH. Then what are you going to have? Tautomerism. This is going to move CH2 nucleophile CH2 C double bond O R1. Now this is called 1,2 addition. This is called 1,4 addition. So you can have a kinetic product and you can have a thermodynamic product. This is the thermodynamic product. Why so? Because you are forming the C double bond O. So under the thermodynamic conditions, you are going to form this ketone. Now this is a kinetic product. The attack to the carbon of the carbonyl is faster. That's why it's called the kinetic product. So some nucleophiles will undergo 1,2 addition. Other nucleophiles, they will undergo either 1,2 or 1,4. Strongly basic nucleophile, for instance, Grignard, lithium aluminum hydride, these are strongly basic, they undergo 1,2 addition. Weakly basic nucleophiles, they undergo 1,4 addition. And I am listing them. So aldehydes and ketones that have a carbon-carbon double bond, they are more stable to start with when the double bond is a conjugation with the carbonyl. And we covered that when we were doing the aldol condensation or the Claisen condensation. After we formed our product in the aldol condensation, and when we are heating it up, we made sure to eliminate the hydrogen that will lead into conjugation, the C double bond C in conjugation with the C double bond O. In fact, if you look at the beta gamma unsaturated ketone, and you are looking at the equilibrium constant, it will equilibrate into the alpha beta unsaturated. The K is 4.8. So the C double bond C, when it is in conjugation with the C double bond O, it is more stable compound. This double bond over here, and you will get this resonance structure. Now, why do you get 1,2 attack or 1,4 attack? You have a partial positive charge on this carbon. You have a partial positive charge on this carbon. So if you are having a nucleophile, that nucleophile can attack either this partially positive charged carbon or this carbon, which is also partially positive carbon. In the 1,2 addition, you're having the nucleophile to attack this carbon. In the 1,4 addition, you are having the nucleophile to attack this carbon. So you have two sites of attack. You have the carbonyl carbon, and you are having the beta carbon. This is your beta carbon. Dipole moments, the trans to butanal is more polar than butanal. You have a greater separation of charges between in trans to butanal than in butanal. In fact, the dipole moment of trans to butanal is 3.7 dBs, while that of butanal is 2.7 dBs. So now let's go to conjugate addition, the 1,2 addition and the 1,4 addition to alpha beta unsaturated carbonyl compounds. 1,2 addition, you have nucleophilic attack at the carbon of the carbonyl. 1,4 addition, you have a conjugate addition. So in the 1,2 addition, you have a direct addition. In the 1,4 addition, you have a conjugate addition. So you have kinetic control versus thermodynamic control. The attack is faster at the carbonyl. The attack at the beta carbon, it gives you the more stable product. This is the result of 1,2 addition. 1,2 addition, if you are adding an HY, Y is going to attack to this carbon and H to the oxygen. So you're getting the 1,2 addition product like we did here. It is formed faster. And that will be the major product under kinetic conditions. So, for instance, when you are having the addition to be irreversible. 1,4 addition, you are having the Y to attack this carbon and the hydrogen at this oxygen, and then there will be tautomerism between the enol and the ketone, which means that this hydrogen is going to go to this carbon. So you will form this product, the ketone. The 1,4 addition product is the thermodynamic product. The 1,2 addition is the kinetic product. So the keto form is isolated. This is the result of 1,4 addition, and it is more stable than the 1,2 addition product. Why? Because C double bond O is stronger than C double bond C. That's why we have the keto to be the thermodynamic product. Now, what are the nucleophiles that will undergo 1,2 additions? Grignard reagents. You have Grignard reagents, you need to go to for 1,2 addition. Lithium aluminium hydride, sodium borohydride, sodium acetylate. Strongly basic nucleophiles, they add irreversibly. That's why they go for the kinetic attack. They will go for the carbon of the carbonyl. So if you have, for instance, this alpha beta unsaturated aldehyde, and you are adding the acetylide, first in THF, then in H3O+, what you are going to have, C- attacking this carbon, you're getting O-, and then O- will be protonated. This is your product. 1,4 addition, it is observed when you are having weakly basic nucleophiles. If you are adding a cyanide, if you are adding a thiolate, if you are adding an ammonia, amines, an azide ion, all of the nucleophiles that we labeled in the substitution as good nucleophiles, non-basic good nucleophile, they undergo 1,4 addition. So these are weakly basic nucleophiles, and they add reversibly. So you will get the tautomerism between the enol and the ketone. So for instance, you are having this alpha beta unsaturated ketone, and you are reacting it with potassium cyanide, you are going to observe this product. You're going to observe the 1,4 addition product. Why? Because you are having first the Cn- to attack this carbon. The double bond is moving here, so you're getting a minus. This is the resonance structure. O- will be protonated by ethanol or acetic acid, and then you have tautomerism. So you have OH, and then the tautomerism will lead into this product. We are having this cyclohexenone, and you are adding a benzyl thiol and hydroxide ion. The thiolate will undergo 1,4 addition. This is going to be your product. So how are you doing it? First, the S- is attacking here. Why S-? Because you have hydroxide ion. S- is attacking here. You're getting the minus. This is a more stable resonance structure. And then this is going to be protonated. And then you have tautomerism. That will be your final product. So let's go over some questions. What is the product of the following reaction? You are having a ketone also. CH3. And you are adding first CH3 MgBr and second D2O. Your colleague is asking, why do we call it 1,4? It's like when we talked about diene, and we talked about 1,2 addition and 1,4 addition. Your functional group is the conjugated diene. Okay? Right here, your functional group is the C double bond C in conjugation with the C double bond O. You have 1, 2, 3, 4 atoms. You are having it 1, 2, it means you are adding them at the 2 adjacent atoms. In this case, it's going to be the carbon of the carbonyl and the oxygen. If you are having 1,4 addition, it means you are adding it at this carbon and at this oxygen. Now, first you are adding that, and then you are having tautomerism that the hydrogen or deuterium or whatever you are having, it is moving to the alpha carbon. Okay, I'm going to close the poll. So 93% got it right. Good job. You are having a Grignard. Grignard is strongly basic nucleophile. It undergoes 1,2 addition. Of course, in these questions, you will have the 1,2 addition as well as the 1,4 addition. And then O- will be deuterated, so the correct answer is 2. Next question. Now, you are adding the phenylthiolate and D2O. Okay, I'm going to close the poll. %, answered 1, 3%, 2, 18%, 3, and the correct answer is 1. The thiolate is a very good nucleophile. It is a weakly basic nucleophile. So it will undergo 1,4 addition. So you are having, in condition number 1, C6H5, SNA. So the phenyl thiolate, this is a weakly basic nucleophile. It undergoes 1,4 addition. And what you are going to form is this intermediate, O minus, double bond, S, C6, H5. You're adding D2O, so you're going to be deuterating the enolate. And then you are having tautomerism, where the enol is going to go into the ketone, and now you have a deuterium over here. So the correct answer is going to be number 1. Any other question? Okay, I'm going to stop right here.